Okay children, this is part B of your refraction of lens. This is the last part of the chapter, magnifying glass and application of lenses. Now magnifying glass is the one which we use usually, is a common thing. We use to read newspapers, we use to read a small print, and simple microscope is another application which is we use in the labs. Okay. So let us go through it. What is the principle of a magnifying glass or simple microscope? What is the objective first? What is the use to observe tiny objects clearly? We prefer to place it as near to our eye as possible, but human eye has a limitation. So in order to see an object by the naked eye, it is necessary to place it at a distance of 25 centimeter from the eye, which is the least distance of distinct vision. Okay, so what is this least distance of distinct vision? That is the distance at which we human eye or normal eye can see an object placed in front of it or an object in front of it. So least distance of distinct vision. This is represented by the letter capital D, and it is numerically equal to 25 centimeter. Now what does this mean? This means in order to see an object clearly by a naked eye, it is necessary for the object to be placed at least at a distance of 25 centimeter from the eye. So this is called the least distance of distinct vision for a normal eye. So what is meant by least distance of distinct vision, D, or define least distance of distinct vision? So you will have to write this as the answer. In order to see an object clearly by the naked eye, it is necessary to place it at least at a distance of 25 centimeter from the eye, which is called which is the least distance of distinct vision, D. Okay. Now the size of the image on the retina is actually determined by the angle subtended by the object at the eye. Okay, the size of the image on the retina, depending upon that we are able to see. Smaller the angle subtended by the object at the eye. Suppose if the object subtends smaller angle at the eye, then smaller is the size of the image on the retina. So it depends upon the angle at which the object makes at the retina of our eye. Now the eye is not able to see an object distinctly or clearly if the object subtends an angle less than 1 minute. 1 minute means 1/60 degrees. Okay, to observe a small object with substance and angle smaller than, so if the object is small, is substance smaller angle. So to observe very small object with substance and angle smaller than 1 minute at the eye, when the place at a distance of least distinct vision, that is 25 centimeters from the eye, we take the help of a convex lens of short focal length. We hold the convex lens in front of our eye. This is a magnifying glass. We hold the convex lens in front of our eye at such a distance that the object lies within its focal length, so that the lens forms an erect virtual and magnified image on the same side and behind the object at a distance d from the lens. That is, when you use this convex lens, what happens? It forms always a virtual image, magnified image, and an erect image. Okay, so that this is the how the magnifying glass helps us. This magnified image now subtends an eye on the angle greater than eye at the angle greater than 1 minute. So it is rightly seen by the eye. So this is the principle of a magnifying glass or reading glass. Okay, children. Now construction of this reading glass you need not learn. Okay. Now the ray diagram of the location of the image of magnifying glass is important. So now in this case, suppose it is a convex lens magnifying glass. Okay, so you keep the object such that it is at the between the first focal point and the lens. Suppose this is the first focal point, the object AB is here. Okay, so then a light ray which comes parallel to this passes through the second focal point, but when you produce it backwards, and a ray through the optical center goes undeviated. Okay, so when you produce them backwards, they meet at this point. So this is the magnified erect virtual image of the object AB. Then magnifying power. Magnifying power of a microscope is given by the formula. Magnifying power is denoted by capital M is equal to 1 plus E upon F, where F is the focal length of the lens and D is the least distance of distinction. So F is the focal length of the lens and D is the least distance of distinction, that is numerically equal to 25 centimeters. Okay, so this magnifying glass is used in a microscope also to see small objects or very small objects. Okay, so is it clear, children? Let me repeat once again. Till now what did we do? We learnt about least distance of least distance of distinction D. That is, in order to see objects clearly, the object should be placed at a distance of minimum 25 centimeters from the eye, then only the eye can see the object clearly. So this distance is called least distance of distinction. Then in magnifying glass, what happens is, why we need a magnifying glass? Because when small objects, it also the size of the image formed on the retina depends upon the angle subtended by the object on the retina. So smaller the object, it subtends smaller angle. So, if the angle subtended by the object on the retina is less than 1 minute, that is 1 upon 60 degree, then the image formed will be very small and we cannot see. So, in such a case, we use this magnifying glass. Now, what does it do? Magnifying glass is nothing but a convex lens. When the object is placed between the focus and the lens, like AB is kept, then a magnified erect virtual image is formed by the lens A dash B dash, which is now which forms an angle more than 1 minute at the retina, and the object can be seen clearly by the naked eye when this image is at the least distance of distinct vision. Okay, so the lens is adjusted in such a way that the image formed by the lens is at a least distance of distinct vision so that the eye can see clearly. Now the next term is magnifying power of a lens. It is given by the formula 1 plus d by f, where f is the focal length of the lens and d is the least distance of distinct vision, that is numerically equal to 25 centimeter. Then you have applications of lenses. Now application of lenses, as you know, the lens of it is used in telescope, camera, slide projector. In all these, the lens used is a convex lens which forms a real and inverted image. Our eye lens is also a convex lens. The eye lens forms an inverted image of the object on the retina. Now, when the eyesight weakens, we use spectacles having either the convex or concave lens. A person suffering from long-sightedness or hypermetropia, that is unable to see the near objects distinctly, wears spectacles having the convex lens, while a person suffering from short-sightedness or myopia, that is unable to see far objects distinctly, wear spectacles having concave lens. Now some people are both short and long sighted. They use either separate spectacles for seeing the near and far objects, or they use the bifocal lens. Okay. In the spectacles using the bifocal lens, the lower part is the convex lens which is used to see the near objects, while the upper part is the concave lens which is used to see the distant objects. Now a magnifying glass is a convex lens of short focal length fitted in a steel frame or plastic frame provided with a handle. Now in the collimator of a spectroscope, convex spectroscope is a optical instrument which is used in the laboratories. There also we use convex lens. A concave lens is used as the eye lens in a Galilean telescope to obtain the final erect image of the object. A single convex lens is usually forms a colored or blurred image due to a chromatic aberration. Therefore, a combination of concave lens with a convex lens is used to overcome such defect. Okay. Now, differentiate between a concave lens and convex lens by touching. By touching, if the lens is thick in the middle and thin at the edges, then the lens is convex, and if the lens is thin in the middle and thick at the edges, the lens is concave. Also, you can identify by seeing the image. On keeping the lens near a printed page, if letters appear magnified, the lens is convex, and if the letters appear diminished, the lens is concave. On seeing a distant object through the lens, if its inverted image is seen, the lens is convex, and if the upright image is seen, the lens is concave. Sometimes this is also asked. This completes the chapter Refraction of Light Through Lens. Okay children, thank you. Take care. God bless you. Hello children. Today we will be doing the numericals in chapter Refraction of Light at Plane Surfaces. So this is your exercise 4A, question number 1. The speed of light in air is 3 into 10 to the power of 8 meter per second. Calculate the speed of light in glass. The refractive index of glass is 1.5. Okay, so now the solution. So refractive index of glass with respect to air is equal to speed of light in air upon speed of light in glass. Okay, so it implies refractive index is 1.5. Speed of light in air is given as 3 into 10 to the power of 8, and speed of light in glass. This is what we have to find out. So implies speed of light in glass is equal to 3 into 10 to the power of 8 upon 1.5. Okay, so this implies 3 into 10 to the power of 9 upon 15. We have multiplied by 10 to remove the decimal. So 3 ones are 3 5s are. So this can be written as 10 into 10 to the power of 8 upon 5. So 5 ones are 5 twos are. So answer is 2 into 10 to the power of 8 meter per second. Okay, so that is the answer, right? So this is your question 1. Now question 2. Now question 2. The speed of light in diamond is 1,25,000 kilometer per second. What is its refractive index? Speed of light in air is equal to 3 into 10 to the power of 8 meter per second. So again, same formula. Refractive index of diamond is equal to speed of light in air upon speed of light in diamond. So implies mu of diamond is equal to speed of light is 3 into 10 to the power of this is speed of light in diamond is given in kilometer per second. So let us write this only as kilometer per second. So 3 into 10 to the power of 5 kilometer per second. 3 to 10 power of 8, so divided by 1000, so it will get converted to kilometer per second. Upon speed of light in diamond is 1,25,000 kilometer per second. So this implies mu is equal to 3 into, if these three zeros get cancelled, though 3 into 10 square upon 125. Okay, so that is equal to 300 upon 125. So 25 goes 5 times, 25 goes not 6, 25 goes 25 ones are 25, 2s are 50. So 12 upon 5. So that will be 5 2s are 10, 5 4s are 20. So 2.4 is the refractive index of diamond. That is the answer. Okay. Now question 3. Question 3 says refractive index of water with respect to air is 4 upon 3. What is the refractive index of air with respect to water? Okay, solution. Now mu with mu of water with respect to air is equal to 1 upon mu of water with respect to air. So mu of air with respect to water will be 1 upon mu of water with respect to air. Okay. In fact, this step is not needed. Straight away you can write solution. It is reciprocal. If you change these two, they will become reciprocal, isn't it? So now we know mu of air. So mu of air with respect to water will be 1 upon mu of water with respect to air. Now mu of water with respect to air is 4 upon 3. So this is equal to 3 upon 4, that is 0.75. So that is the answer. Okay. Now question 4. A ray of light of wavelength 5400 suffers refraction from air to glass. Taking mu of glass with respect to air as equal to 3 upon 2, find the wavelength of light in glass. Now solution. Now here we know velocity is equal to f lambda. Okay. Now mu of glass with respect to air is equal to velocity of light in air upon velocity in glass. Okay. Now, so this implies this is given as 3 upon 2. This is f frequency in air into wavelength of light in air upon frequency in glass into wavelength in glass. But frequency remains unchanged in refraction. So, but frequency of air is equal to frequency of glass. Frequency does not change. Okay. So, it implies 3 upon 2 is equal to lambda of air upon lambda in glass. So, lambda in glass is equal to lambda in air into 2 upon 3. So, implies lambda in glass is equal to lambda in air is 5400 into 2 upon 3. So, 3 ones are 3 eights are 0 0. So, 3600. Okay. Now, exercise 4B. First numerical. A ray of light incident at an angle incidence 48 degree on a prism of refracting angle 60 degree suffers minimum deviation. Calculate the angle of minimum deviation. So, solution. Now, what is given? Angle of incidence I is 48 degrees. Angle of the prism A is equal to 60 degrees. What is asked? Angle of minimum deviation. Okay, so now we know the formula. Angle of minimum deviation is equal to 2I minus A. So, delta minimum is equal to 2 into 48 degrees minus 60 degrees. So, .36 degrees is the answer. Now, second question. What should be the angle of incidence for a ray of light which suffers a minimum deviation of 36 degree through an equivalent prism. Through an equilateral prism. In an equilateral prism, you know A is equal to 60 degrees. So, solution. Angle of deviation, minimum deviation is 36 degree and angle A is equal to 60 degrees and angle I, how much we have to find. So again same formula, delta minimum or angle of deviation is equal to 2I minus A. So 36 degrees is equal to 2 into I minus 60. So implies 2I is equal to 36 plus 60 implies 2I is equal to 96 implies I is equal to 96 upon 2, 48 degrees. Answer. Now exercise 4C. Question 1. A water pond appears to be 2.7 meter deep. If the refractive index of water is 4 upon 3, find the actual depth of the pond. Okay. Now, we know refractive index mu is equal to real depth upon apparent depth. So this implies refractive index is given as 4 upon 3. Real depth we don't know, but the pond appears to be 2.7 meter deep, means apparent depth is 2.7. So implies real depth is equal to 2.7 into 4 upon 3. Real depth is 3.6 meter. A coin is placed at the bottom of a beaker containing water, and mu of water is 4 upon 3 to a depth of 12 centimeters. By what height the coin appears to be raised when seen from vertically above. A solution. Now what is given? Mu of water is given as 4 upon 3. Real depth 12 centimeter. Apparent depth we have to find out. So we know mu is equal to real depth upon apparent depth. So implies 4 upon 3 is equal to 12 upon apparent depth. So implies apparent depth is equal to 12 into 3 upon 4, that is 9 centimeter. So the coin appears to be raised by 12 minus 9, that is 3 centimeter. Okay. Now question 3. A postage stamp kept below a rectangular glass slab of refract. A postage stamp kept below a rectangular glass slab of refractive index mu is equal to 1.5 when viewed from vertically above it appears to be raised by 7 millimeter. Calculate the thickness of the glass slab. Okay, so we know mu is equal to 1.5 mu of glass. Now let the thickness of the glass slab be x millimeter. Okay, so stamp is raised by 7 millimeter. So that means observed or apparent observed depth is equal to observed depth means apparent depth is equal to x minus 7 millimeter. Now refractive index mu is equal to real depth upon the observed depth or the apparent depth. Okay, so implies now refractive index is given as 3 upon 2, real depth is x, observed depth is x minus 7. Okay, so this implies 3x minus 21 is equal to 2x, implies 3x minus 2x is equal to 21, or implies x is equal to 21 millimeter. So what is our x? The thickness of the slab, or that is equal to 2.1 centimeter. Thickness of slab 2.1 centimeter. So that is the answer. So there are no numericals in exercise 4D. So these are the numericals in the chapter Refraction and Plane Surfaces. Okay. So these questions are very simple. I hope you understood. These real depth and apparent depth are somewhat important from the examination point of view. but this chapter is more important for the diagrams. Okay children, so let me stop here for today. Take care. God bless you. Good evening children. This is Vanashri ma'am. We will be doing the numericals of the chapter Refraction of Light Through Lens. Okay, so this is your exercise 5C. There are no numericals in A and B. So in exercise 5C, you have the question 1 says, at what position a candle of length 3 centimeter, so 3 centimeter is the size of the object actually, okay, be placed in front of a convex lens so that its image of length 6 centimeter can be obtained on a screen placed at a distance of 30 centimeter behind the lens. So its image of length 6 centimeter, that means what, and also we have to find focal length. So what is given, we have to find the object distance, that is how far first of all the object has to be placed, so that is u we have to find. Size of the object 3 centimeter given, size of the image, that is I, size of the object is O, that is 3 centimeter given, size of the image I will be minus 6 centimeter. Why? Because in case this is what type of lens is this? This is a convex lens. So in case of a convex lens, the image will be real image. So it will be minus 6 centimeter. Okay. Image distance V 30 centimeter given. So magnification is image, size of the image upon size of the object, that is also equal to object image distance upon object distance. So minus 6 upon 3 is equal to V is 30 and you have to find out. So minus, so when you cross multiply, minus 6u is equal to 3 into 30. So u is equal to 3 into 30 upon minus 6, that is minus 15 centimeter. So that means the candle should be placed 15 centimeter in front of the lens, on the left of the lens, that is here. Okay, so minus 15 centimeter implies on the left. Suppose if this is the coordinate system, I have told you, if this represents the lens, then the our image is minus 15, image distance we got minus 15, so it must be kept on this side, and real images are always formed on the same side as the object, that is this side. So the other things, whichever actually is formed on this side will be minus, this side will be positive. Okay, similarly on the upper, that is erect images on the right side will be positive, erect image on the left side will be negative, inverted image on the left side will be negative, inverted image formed on the right side will be positive. Okay, so now we have to find out focal length. So 1 upon f is equal to 1 upon v minus 1 upon u for convex lens. So implies 1 upon f is equal to, substitute the values, so you will get, on some simplifying, you will get 1 upon f is equal to 1 upon 10 by taking the cross multiplying 15 plus 30 upon 15 into 30. So this way if you simplify, so f is equal to 10 centimeter. Okay, now the second question. A concave lens forms the image of an object kept at a distance of 20 centimeter in front of it. Concave lens, remember it is a concave lens. 20 centimeter in front of it at a distance of 10 centimeter on the side of the object. So on the same side as the object it is formed. Okay, what is the nature of the image? Find the focal length of the lens. Now concave lens forms always a virtual image. So image will be virtual, erect and diminished. That will be the nature of the image. Okay, u and v both are negative for a concave lens. So u is minus 20, v is minus 10. So focal length will be 1 upon v, f of 1 upon f is equal to 1 upon v minus 1 upon u. So you substitute the values, simplify, you will get 1 upon f is equal to minus 1 upon 20. So f is equal to minus 20. So focal length is 20 centimeter. Okay. Next, the focal length of a convex lens is 25 centimeter. At what distance from the lens an object be placed to obtain a virtual image of twice the size. Twice the size means it is a magnified. So magnification is 2 actually. M is equal to 2. So M is 2 because it is 2 times bigger. So magnification is twice 2. M is equal to V upon U. So substitute M is equal to 2. So 2 is equal to V upon U, or V is equal to, if you cross multiply, 2U. So if you substitute 1 upon F is equal to 1 upon V minus 1 upon U in that formula, if you substitute V is equal to 2U, you will get, and F is 25 given. So 1 upon 25 is equal to, you will get 1 upon minus 1 upon 2U. Okay, this gets cancelled. So minus 1 upon 2U. Followed? We just cross multiplied. 1 into U, 2U into minus 1, 2U upon 2U into U. So this U gets cancelled. So 1 upon minus 1 upon 2U. So if you cross multiply, minus 2U is equal to 25. So U is equal to minus 12.5. Now the minus sign implies the object is placed on the left side of the lens at a distance of 12.5 centimeter from the lens. Okay, now question 4 is homework for you. Where should an object be placed in front of a convex lens of focal length 0.12 meter? This is actually equal to 12 centimeter, nothing new. To obtain a real image of 3 times, that means magnification is given, M is equal to 3. So that what we have to find? We have to find where should an object be placed. So we have to find out U. So M is given, you have to find out U. You are already given F. So this is similar sum, so you can do it. The answer is given to you. Try it. If you don't get, then you can ask in the group. Now question 5. An illuminated object lies at a distance of 1 meter from a screen. A convex lens is used to form the image of the object on a screen placed at a distance of 75 centimeter. So an illuminated object lies at a distance of 1 meter means that is 1 meter from the screen. Mind it, this is, don't take it as directly as object distance. This distance 1 meter is from the screen. And find the focal length and the magnification. Okay, so let us start solving this sum. So now that means here, suppose this is the lens. Okay, so this is the screen and this is the lens. Now illuminated object is kept here. Okay, now the question says an illuminated object is kept lies at a distance of 1 meter from the screen. So this whole thing is 1 meter. That means 100 centimeter. Okay. A convex lens is used to form the image of the object on a screen placed at a distance of 75 centimeter from the lens. So the screen is 75 centimeter from the lens. So that means this distance is 25 centimeter because the total is 100. Okay. So we have to find out what? The focal length of the lens and the magnification. Okay. So now 1 upon F is equal to 1 upon V minus 1 upon U. So these are all similar sums, only little bit changes. So 1 upon 75 implies 1 upon F is equal to 1 upon 75 minus 1 upon minus 25. Okay. Why minus 25? Because it is on the left side. Okay. So now, so implies 1 upon F is equal to 1 upon this is 1 upon 75 plus 1 upon 25. Okay, so this implies 25 plus 75 upon 75 into 25, that is 100 upon 75 into 25. So 25 ones are 25 fours are. Okay, so that is equal to, so this implies f is equal to 75 upon 4. So that implies 4 ones are 4, 35, so 4 eights are 32, then 3 remains, so 4 sevens are 28, and 4 fives are 20. So f is 18.75. Now you are asked to find out magnification. Okay, this is one answer. Then magnification m is equal to v upon u, that is v is 75, u is 20 minus 25, so it will be minus 3. So that means magnification is minus 3 means what? Negative sign shows that the image is formed inverted and real, and it is diminished also. Okay. So image is real and inverted. When it is inverted, then only it will be in the negative part of the y-axis.